Okay, hi guys. So in this lecture, we'll be discussing on the analysis of the length of a gas, or rather air column trapped in liquid mercury. So let me put down the heading first. So we'll be discussing on analysis of length of gas or air column trapped in liquid mercury. Okay. So suppose we have a vessel which is partitioned with the half, let's say L1 is partitioned into having some gas molecules here, okay, and L2 is partitioned having some liquid mercury, okay. So for a gas, we can say that and in the second case, let's say this was length L. In the second case, what actually is happening is, for the same vessel we are actually inverting it to have it in a vertical position, so that liquid mercury comes in the upper side of gas. Okay, so here we have again L length here and L2 length here, and P of ATM is also acting on liquid mercury. So for a gas, we can say that as number of moles and temperature is not changing, we can say that P1 V1 equal to P2 V2. Okay, V1 is the volume of the gas here and V2 is the volume of the gas here. So we can write that P1 times A is the cross section area of the vessel times L1 would be equals to P2 into A into L2. A and A gets cancelled. So as a result, for a gas at same temperature, okay, so at the same temperature, as the number of moles are not changing, so N and T are constant, hence we can equate P1 V1 with P2 V2. So we can simply write P1 L1 would be equal to P2 L2. Okay, and here P of gas would be nothing but P of ATM plus P of HG. Okay, so this is nothing but P2. P2's value would be summation of these two. Let's take some example on the same. Suppose we have a beaker which is placed at some degree to the vertical. Okay, so let's say it is to the vertical or to the horizontal, either way you can term it. So suppose we have this making angle theta with the beaker, and we are also having some liquid mercury filled at the top of the beaker. P of ATM is also acting here, okay, and we have some gas molecules filled inside the beaker. This is gas molecules, okay. So this is length L, so we can write that P of gas, pressure of gas, would be P of ATM. P of ATM does not change with the change in the angle of the beaker. P of ATM is always there and is always present in as 1 ATM. Howsoever we change the angle of the beaker with the ground, it does not depend on that. So P of ATM plus P of HG. P of HG would be in this direction. Okay, so what will we do? So if you look at it, so center of mass is here of the gas, let's say, and mg is here, okay, and if pressure is acting here for the hg, so P of ATM plus P of ATM is constant in any of the angle, it does not matter, and P of hg is in this direction, so we have to convert it in this direction. Angle here is theta, so we can write P of hg sin theta. Okay, so P of hg sin theta would be the total pressure. So total pressure would be P of ATM plus P of hg sin theta. Okay, Now let's see what happens for this case, where we have a beaker something like this, inverted beaker. Okay, and in this beaker we have this as Hg, and here we have gas particles. So we can write that P of ATM is actually would be equals to P of gas plus P of Hg, and in other words P of Hg, a gas can be written as P of ATM minus pressure of mercury. Okay, we can see here that pressure of mercury would be exerted in the downward direction, pressure of gas would be exerted in the downward direction, and similarly pressure of Hg would also be exerted in the downward direction, and on the opposite direction P of ATM is there to cancel them out. Hence P of ATM is equals to P of Hg plus P of gas. Okay, so now let's see our next topic, which is types of vessel. Okay, next we are going to see types of vessel. Okay, so first we are going to discuss about open vessel, which can be any of the following. We can have something like this. Okay, it is open, which is having volume V at temperature T. We can have some shape like this of a vessel, again with volume V, and can have temperature T, or we can have simple some vessel like this. So in this type of vessel, PV equals to constant, or you can write that N1 T1 would be equals to N2 T2, as pressure is same in all the cases, which is PATM. Volume is same in all the cases. This is at temperature T1, this is temperature T2, this is at temperature T3. Volume of the vessel is same in all the cases that has been given. Hence PV equals to constant, and we can equate the number of moles and temperature with each other. Second, we can have closed vessel or closed system. So in closed vessel we can have situations like, first it can be a non-rigid vessel. So example of a non-rigid vessel can be something like this. Some gas molecules are there. These are not gas molecules, these are too big for a gas molecule. Yeah, some gas molecules are there, and we have applied some pressure on the top of it. We have some partition or some boundary. So non-rigid vessel can be a tube type or a piston type. So this is a piston. Okay, next let's discuss about what is called as a rigid vessel. Okay, so before that I'll just like to say that here in any of the type of the non-rigid vessel, n we are considering as constant. So as n is constant, we can equate P1 upon T1, P1 V1 upon T1 as equals to P2 V2 upon T2. P1 V1 here and P2 V2 upon T2. Obviously the P1 V1 and T1 are, let's say, for the tube type, and P2 V2 upon T2 is for the piston type. We are just changing the storage type of the same number of moles of gas. Okay, so next let's discuss about rigid vessel. So in rigid vessel, what happens is volume remains constant. Okay, so work done on that vessel would be 0. Okay, so as the volume remains constant, what can we write? We had P1 V1 upon T1 equals to P2 V2 upon T2 from the previous reaction. So here, as V1 would be equals to V2, we can cancel them out, and we can simply write P1 upon T1 would be equals to P2 upon T2. Okay, next let's look at some of the chemical reactions. Okay, so in chemical reactions, what is the general rule of thumb? In chemical reactions, we can see general rule of thumb as P1 V1 upon N1 T1 is equals to P2 V2 upon N2 T2. This is for any equation, any gas having ideal gas having any change in vessel type or pressure type or any other type. This is the equation which always remains true. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing some more important concepts on diffusion and effusion, but before that we'll also be seeing the payload of a balloon concept. It's a small concept, so we'll discuss all those things in the next lecture. So till then, good luck and goodbye.